Okay, this question is a little bit like example 2.7 on page 60 of the text, but I've changed the values just to make it a little bit more interesting. Now, in the previous problem, we did a very simple problem where you were given a force and a distance, and they asked you to calculate the moment. In this instance, they've given you your final moment, which is a force times the distance. They've asked you to calculate the force required, so we don't know what the force is to get that moment. Okay, so best way of doing this is write down your equation. Moment is equal to force times distance. Okay, we know that we're dealing with a positive moment because the force is going to make this whole thing turn clockwise. We know that we're given these values. Okay, we can do a free body diagram. We've got a pivot. Let's go FBD. Free body diagram. Got a pivot. We've got a force which we're trying to work out. The force is at 90 degrees, so we can use our distance of the arm. We're going to convert that distance to meters straight away, 0.14 meters is our distance. Okay, we know that we're trying to work out force. So all we have to do is arrange the subject of this equation. Okay, so if we want to get force by itself, we have to multiply by 1 on d. On this side to get rid of the d, so the d cancels down. So let's do that up here. Let's use a better colour so we can actually see what we're doing. So trusty purple. We say force is equal to moment over distance. So we go force is equal to, well, we know our moment is equal to 50 Newton meters. We know our distance is equal to 0.14 meters. Put that up our free body diagram. So we're going to say 50 over 0.14. Therefore, force in newtons is equal to, get out our calculator and go 50 divided by 0.14, and that gives us a value of 357.14 newtons approximately. So this type of question is just about changing the subject of the equation. So that's pretty much as simple a question on moments you could possibly get. And remembering, a moment creates a turn. Okay, that's what moments are about. If you've got a force acting on a pivot at a distance, it'll create a turn. Now, obviously, if the force is acting through the pin, it's not creating a turn, is it? So you have to have a perpendicular distance, and it can't be acting through the pivot point. If you've got the line of action running straight through the pivot point, it's not going to cause a turn, and therefore you don't get a moment. There'll be a force, and there'll be a reaction force, but there won't be a moment. Okay, we will do the wheelbarrow question next. So this question is very much like the one on page 60 and 61. We're going to look at both methods. I have changed the values somewhat, just to keep it fresh, and I will put some other examples on this page with changed values so we can practice doing the question. But this question really examines trying to understand distance, perpendicular distance for an applied force, okay, when you're calculating a moment. Remember, moment is force times distance, but it's perpendicular distance, okay? And we discussed that before this video. We're going to do that again. Hopefully, if you didn't understand that discussion, it'll start making better sense now. Okay, so a wheelbarrow has handles inclined 20 degrees to the ground. So first thing you might want to do is draw a little line out here and just throw that angle in there, 20 degrees, okay, so that you know it's there, okay? The user is lifting with a vertical force. Find the force required with each handle to lift the load of 50 kilograms. First thing you need to know is that quite often people talk about their weight. They say, I weigh so many kilograms. Well, we know weight is not actually kilograms. Mass is kilograms. People should actually be saying to you, what is your mass? But that sounds a little bit weird. So In physics and in engineering, when you see weight, it's equal to mass by gravitation. And we know in this course, if you're doing a physics course, I usually go 9.8 meters per second squared. Is that gravitation? But for this course, we say it's 10. Okay, so we're going to say 50 times 10, you know, our weight force is equal to 500 newtons. Other thing to remember about mass is no matter what's happening, you've got a weight on a plane, the mass is always acting straight down, okay? Sorry, mass, the weight is always acting straight down. Weight force always acts straight down, okay? So that's another thing to remember in this course that will get you out of trouble quite often. So in this instance, it's acting straight down, and our lifting force is acting straight up, okay? But the problem with this problem is that when we're looking at our distance here, our distance is not perpendicular to its distance. So how do we find the perpendicular distance? Well, you remember that it has to be 90 degrees to the pivot. So remember the first thing I said to do is take your line of transmissibility, this is straight up and down, and you might want to just make sure that you extend those lines, okay? Once you extend those lines, let's see if we can find a better marker than that. Once you extend those lines out, you have to work out where our pivot will hit 90 degrees. Okay, so we're here, okay, we start dropping our line. When we get to the horizontal, that's where our line's at 90 degrees, okay, with the force that's being applied. So let's grab our purple one, because that seems to be the only one that's working. And we'll draw our line in. Okay, so we know that's 90 degrees. We extended our line, and mass is equal to, moment is positive is equal to force by perpendicular distance. So we need to work out this distance from here to here. Okay? What is that distance? Well, we're going to use our trigonometry to do that. We know the length of the arm is actually 1400, and we know we don't know this distance, but we know this angle. Okay, this is the hypotenuse. So let's draw that triangle here. Argument's sake, we know that our force of effort's here. That's why we extended that line. We know this line is the barrow arms, and they're 1400 millimeters. So we're trying to work out this distance. So you might want to change this to meters straight away. It's 1.4 meters. Okay, that's how long the thing is. We know that this angle is 20 degrees. We need to calculate that distance there. Okay, so SOHCAHTOA, adjacent on hypotenuse, is cos. So we go cos 20 degrees is equal to d over 1.4. Which is this distance here, d, that's what we're trying to work out. Therefore, d is equal to 1.4 by cos 20. Get our calculator out. Is equal to 1.32 meters. Okay, so that's calculated that moment for this force of effort. Okay, but is that the only moment that we've got happening? So we know that this is going to be an anti-clockwise situation. So we're going to say our force of effort, our moment is equal to force times distance. Okay, we actually have a situation here where It's an equilibrium situation. Okay, when you lift the wheelbarrow up, you're applying a force this way and a moment this way, but the weight is applying a moment in the opposite direction. Okay, so it's what they call an equilibrium situation. So basically what happens is those moments, if you want to hold the barrow so that it doesn't drop or raise or keep raising, you need to have it in equilibrium. Okay, so in other words, the force that wants to make the wheelbarrow lift is being opposed by the force of the weight, okay, so that wants to make the wheelbarrow fall. They cancel each other out, okay? So this is something that you're going to use a lot when you do truss analysis, the idea of equilibrium, okay? So basically what that means is this anti-clockwise moment we're talking about here, okay, has to be opposed by the clockwise one being caused by the weight, okay? So the weight's pulling us down, making us go this way, and our lifting force is making us go that way, and they cancel each other out. Okay, so this is working out that you're going to have to use all of the time when you're dealing with an equilibrium situation. Okay, so this is quite a complex problem. So new concepts to get your head around the concept of equilibrium. So we're going to go clockwise is positive. We're going to go sigma moments is equal to 0. In other words, the sum of moments is equal to 0. Okay, so then we're going to go 0 equals, and let's add up our clockwise ones first. We have 500 newtons of the weight force pulling it clockwise. So we know that moments are equal to force by distance, so M equals FD. So we're going to go, for this one, we're going to go 500 times, what's the distance? The distance is the perpendicular distance from the pivot point. And in this instance, they've given us the perpendicular distance, okay? It's 400 millimeters. So we need to write that 400 millimeters as meters. So it's 0.4. And it's going to be positive because it's clockwise. And then we're going to subtract, okay, our counterclockwise. And we worked that out when we said it's equal to the force of effort, which is this one acting straight up, okay, just here, multiplied by the perpendicular distance. And we calculated that distance here, okay, which was 1.32 meters by 1.32. So then we go 0 equals 500 by 0.4, which I think is 200, minus 1.32 times the force of effort. Now we can take that force of effort over the other side, the equal sign, it becomes force of effort is equal to 200, we divide by the 1.32. Force of effort equals 151.52 newtons. That's our force of effort. So we've introduced a new concept here, the concept of equilibrium. Okay, now when we do truss analysis, if something's not turning and it has a moment applied, it's because there's another moment cancelling it. Okay, so if you don't cancel that moment, the thing will just keep turning. So we need to, if we have an equilibrium situation, it's always going to be a stationary situation. And you will find that in most structures and most problems that you're dealing with in this course, that working out that I just did there, sum of moments is equal to 0, and then you work out your clockwise and anti-clockwise, you can find an unknown. In this case, we found the force of effort that we didn't know. It's required in both hands to lift that barrow and keep it stationary. Okay, it's keeping it balanced essentially. Okay, in an equilibrium situation. So that was the first method where we were using our perpendicular distance. Okay. Now, what happens if we decided that we wanted to use this length here? We should end up, if we do the same working out, we should end up with the same result, 151.52 newtons. Okay. So if you don't end up with the same result, you'll know that you've actually got it wrong. I want to write the result 151.52 newtons in the corner of the board. And basically what needs to happen is we need to make sure that when we use the second method, we get the same answer. If we don't, we've done something wrong. Okay, so let's get this all rubbed out. And make sure that you follow this type of laying out of your working out as well. Okay, so when we're giving this problem here, we're going to use components of vectors this time. Okay, so we want to work out the component that is at 90 degrees to this arm, which is 1400, and that will then give us a horizontal component as well, or not horizontal, a component that's parallel with the arm, okay, 20 degrees, and one that's at 90 degrees to the arm, okay? So we need to work out those components. So if we do a little breakdown here, just so we can see what's going on, we've got 20 degrees, we've got our force of effort acting straight up. The one that's at 90 degrees to the arm, okay, is going to be cos 20 times Fe, and the one that's acting straight out of the arm, it's not that long, because we need to break it down, that would be sine 20 times Fe, okay? So we're going to use the same working out. Always good to write down formulas you know, so you might want to write down moment equals force times distance, just let them know you know that. And then we need to say, well, this is an equilibrium situation still, so we're going to say clockwise is positive. Sigma moments is equal to 0. In other words, the sum of moments is equal to 0 because it's an equilibrium situation. Okay? Always need to write that down. You'll see example after example in your textbook using this working out. Okay? It's what the examiner is looking for. And we say 0 is equal to, let's do our clockwise first, and we set our clockwise situation. You can draw a free body diagram. I think that's always a good thing to do. So let's draw a free body diagram of the situation. Pivot is P. Okay, our force acting at 90 degrees, we've already said, is cos 20 times Fe. This is degrees. This is sine 20 Fe. This is 20. We've got a weight force acting down, straight down, 500 newtons. We've got a distance here, we've already said, of 0.4 meters. All good so far? And then we know the distance of this arm is 1.4 meters. We've done our free body diagram. I'm going to write that underneath here, sine 20 Fe. So now we need to do exactly the same working out, except that instead of using this distance here, because this is at 90 degrees, we can do the same thing. So we say, if the sum of moments, positive moments, is equal to 0, we say 0 is equal to, go clockwise first, and we know that it's 500 by 0.4, 500 by 0.4, okay, minus, because we're going, this is going clockwise, so it's positive, anti-clockwise is negative. We're going to say cos 20 Fe times 1.4, okay, because it's 1.4 meters. So the working out looks a little bit different, okay? Let's work that out now. We go 0 equals 200 minus cos 20 Fe is 1.4. Let's get our calculator out and go cos 20 equals times 1.4 equals, we end up with 1.32. So So 0 equals 200 minus 1.32 Fe. Take this over the other side to make it positive and make it the subject of the equation. We end up with 1.32 Fe equals 200. Divide by 1.32. Fe equals 200 divided by 1.32. And that equals 151.52 newtons. And guess what? It's the same as the original answer. Okay, so that's the two methods that are shown in the textbook. Read pages 60, 50, 60 and 61. I'll write it up here. And have a crack at the question that's in the textbook. Write all this down and make sure you understand fully the idea of perpendicular distance. Okay, so if you need to watch the video a few times and draw some diagrams and think about it, that would be helpful. But that's a concept you really need to grasp, what that perpendicular distance is. And like I said, finding perpendicular distances, you just extend the line of transmission and then move the arm until you find where it intersects at 90 degrees to that force. Okay, so extend the force, transmissibility of forces, move arm until you hit 90 degrees with that line that's made. That's your perpendicular distance from the pivot. Okay, two methods. One, we use the actual length of the arm and component of vectors. Okay, now, like I said, you don't need to worry about this force here. It's acting here when you break it up into vectors because it's pulling, it's going, if you extend its line, it runs through the pin. Okay, if the line of force is running through the pin, it doesn't create a moment. It's kind of like trying to open a door. Instead of pushing on the door to open the door, you start pulling on the hinge this way. Okay, the door's not going to open. That's the best way of thinking about it. Anyway, I hope that helps. But have a read of those two pages, pages 60 and 61 in Copeland, and have a crack at that example. And hopefully we will be on our way to understanding moments, and some of moments clockwise and anti-clockwise. We have a situation of equilibrium. Bye.